And I'll just start by providing both of these proofs so you can check with your work yesterday to see if you did something similar. Now, in the first proof, we talked about this one already, but this is a good example of when you're deciding what to change things to, you have a choice with cotangent. Should I change cotangent to 1 over tan, or should I change things to cos over sine? And what should I choose when I have that option? Well, in this, it really depends on the entire proof. So in this proof, up till now, the right-hand side is cos. The only thing I can change cosecant to is 1 over sine. So in deciding, should I change cotangent to 1 over tan or cos over sine, most of the time you're going to choose to change it to cos over sine. Because one of our key strategies that we're going to learn is changing things to sine and to cosine. The only time I would change it to 1 over tan is if I would look on the other side of the equation and say, the other side is full of tan, my side can be changed to all tan. If everything is tan, it would work well. But in this case, the other side is cos. So it makes more sense to change the cotangent to cos over sine. And then I have a fraction divided by a fraction. So to write this as a single fraction, I can multiply by the reciprocal. Check if any factors are the same. These ones are, so they'll simplify. And sure enough, we get cos theta. So my left side is equal to my right side. I'm done my proof. For the second proof, again, I'm looking at this equation. Can I change everything to sine and cos? Well, I can change everything to cos because secant is 1 over cos. Again, at this point, we're going to use that strategy of once I've changed things to sine and cos, can I write both sides as a single fraction? Well, the left side is cos, which is cos over 1. It's already a single fraction. But the right side has a fraction inside of a fraction. And when you have fractions inside of a fraction, what we're going to want to do is create one fraction in our numerator, one fraction in our denominator. Right now, I don't have one fraction in my denominator. Draw a big long line here. But I could get one fraction in my denominator by adding fractions, which means getting a common denominator. And once I get a common denominator of cos, I could add the tops, which will leave me with cos theta plus 1. Now the top is 1 plus cos theta, and technically, when you have just a single thing on the top of your fraction, you could make that a single fraction by making it all over 1. So I have a fraction in my numerator, a fraction in my denominator, a fraction divided by a fraction. You can multiply by the reciprocal, so what does that look like? I'd have 1 plus cos theta all over 1 times by the reciprocal, cos theta over, and I'm going to write that cos theta plus 1 as 1 plus cos theta because adding doesn't matter the order. Now whenever you add and subtract, those things get grouped together as a single factor. So this would get grouped together as a single factor. And now that we're multiplying everything, we check, do we have any factors that are identical? Yes. So those could simplify. And we're just left with cos theta. So our left side is equal to our right side. And we're all done. Now, we had proven these the other day. You had worked on them on your own, so hopefully your proofs were similar and you were able to get these. But I wanted to rewrite them because part I says determine the non-permissible values of theta. It should actually, in my opinion, have prove the identity first and then determine the non-permissible values. because our non-permissible values, we're going to check in multiple places in our proof to see what our non-permissible values are. So for non-permissible values, what do we know? We know that we're not allowed to take square roots of negatives. We know that we're not allowed to divide by 0. There's no square roots in these proofs, but there is dividing. So we're going to look at our first proof and check where are all the places that we divide. Well, take out a highlighter. We're dividing by cosecant there. We're dividing by sine here. We're dividing by sine here. We're dividing by sine here. So those are all the places that we divide. We're not dividing by anything on the right-hand side. But because we're dividing, we have to make statements that say sine theta can't equal 0, because then it would cause us to divide by 0. Cosecant theta cannot equal 0. So this is one thing that's not allowed. This is another thing that's not allowed. Well, let's figure these out. When is sine theta equal to 0? And we're going to write our general solution for this. So if I'm solving sine theta equals 0 between 0 and 2 pi, when does that happen? Your y-coordinate equal to 0. Theta cannot equal 0, pi, and 2 pi. So you could take all three of those and say plus 2k pi. But for this one, do you remember the shortcut for writing all of those together? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Theta cannot equal k pi, where k is an integer. Now, for solving cosecant theta cannot equal 0, cosecant theta is 1 over sine theta. And if you're trying to solve 1 over sine theta equals to 0, the only time a fraction is equal to 0 is if the numerator is equal to 0. That's the only time a fraction can equal 0. Is the numerator ever going to be 0? No, the numerator is always 1. So this one is never 0, and this is the only non-permissible values for the first question. It is Pi Day. It's March 14th. So I'll show you something fun for Pi Day. Maybe you've seen this before. Pi is a decimal. When people say pi is a decimal, what do they say? 3.14. So I'm going to write 3.14 sort of in like computery kind of font. Okay? And we're going to take that 3.14 and we're going to flip it over. What does it spell? Pi. Yummy. Have you seen that before? No? Okay. Well, happy Pi Day. Okay. Our second one. Non-permissible values. Again, we want to check throughout this whole thing, where are we dividing? Well, we're dividing by 0. Well, we can't divide by 0, but we're dividing here, we're dividing here, we're dividing here, and we're dividing here, even though it got canceled out. Those are all the places that we're dividing in this question. So what does that mean? That means for this question, we have that cos of theta can't equal 0. and cos of theta can't equal -1. We want to write all the non-permissible values for this one. So it's like solving a general solution. When is cos of theta, and for cos of theta equals 0, when we studied the graph of cos the first time, you might remember that we wrote the zeros of cos as odd numbers times pi over 2. And we wrote that as 2k plus 1 times pi over 2. And then we also saw another pattern that said we could write it as pi over 2 plus k pi. And usually those are things that we forget. Or it's like, if I say, what are the zeros of cos? It's not the first thing that comes to your mind. So now that we've done a little bit of work in Chapter 7, and we've learned about the general solution, I actually find figuring out the zeros of cosine easier if you think about the general solution. If I'm solving where is cos equal to 0, okay? From 0 to 2 pi, when is cos equal to 0? When is your x coordinate 0? At pi over 2 and at 3 pi over 2. So if I wanted to write all of the zeros, I could take my answers from 0 to 2 pi and write my general solution plus 2k pi plus 2k pi. And that might be easier than saying, oh, I have to remember that the zeros of cosine are 2k plus 1 in brackets times pi over 2. Because I might not remember that. But I can resolve it using the general solution. When is cos theta, when is your x coordinate -1? What angle gives you that? Well, the only angle is pi. So we could write the general solution for that as well. And we have listed all the non-permissible values of this question. Perfect.